Okay, so the main purpose of today's lesson is to deal with multiplying and dividing things that are already in our polar form. So there's ways to deal with that rather than having to convert it to rectangular form and then convert it back to polar form. We already know how to multiply and divide things that are already in rectangular form. We did that in our first lesson where we did 1 plus I times 2 plus I. We just multiply it all out and we have a real component and an imaginary component. Same thing with dividing. If I have 1 plus I divided by 1 minus I, we would multiply by the conjugate and then we would represent it in a real component and an imaginary component. So again, there's a way to deal with the product and quotient of two polar form too, rather than having to convert it in that same way. So you do need to know these ones, but it's really easy to actually memorize them. The R values that we have, which are just numbers like 2 and 4 or whatever, those get multiplied out front, just like it makes sense because we're multiplying these two things. But then the angles, instead of multiplying this value and this value, we keep the cis part and then we add the two angles. So think about it like you would exponents, like if I do x squared times x to the third power, you don't multiply the exponents too, you add them. So that's the way to kind of remember it. So same thing with our quotient, like our R values just get divided. So R1 divided by R2. And then our angles, rather than getting added together, we subtract them. So just again like exponents, x to the 7th over x squared, you would subtract the 2 and get x to the 5th. So it's kind of like that idea. We could derive these, and what we'd have to do is sum and difference stuff, but just trust me that these actually are, and maybe I'll show you that at another time, these are the product and theorem, or product and quotient theorems do apply and do allow us to deal with our polar form and our complex numbers. Okay, so the first couple examples, we're going to use that product theorem in action. So the first one, again, it's really, we just have to take our R values, which this would be R1, this would be R2, and we multiply our two values. So R1 times R2 is going to be 6. And then the angle that we have in here, we have to add the two angle measurements, our theta 1 and theta 2. So 45 plus 135. So I'm going to simplify that. And 45 and 135 is 180. And we want to answer this question in rectangular form. Right now we had this thing in product in polar form, so we want to represent this in rectangular form with our real component and our imaginary component. So what that means is we're going to draw a diagram, and we're going to represent this R and this theta, our length of our vector and the direction of our vector. So we're at 180 degrees, which is on our x-axis, and the length here is 6. That would be R. But be careful, because going negative or going 6 and 180 degrees means that our x value is actually -6. So when we represent our real component, which is this -6, everything on our x-axis, remember rectangular form is x plus yi, this x value is going to be -6. And then we don't have any y component because we're not going up or down, we're just on our axis. So this would be 0i. So -6 in total. So I think it's kind of crazy, and maybe you don't think this way, but the fact that we have stuff that obviously has some imaginary component in it and obviously has some imaginary component in it with a direction that's not on our x-axis, and then we multiply these two things and we somehow get this real answer back out. So things that wouldn't exist in the real number system, now the product of them actually does exist. So I think that's kind of crazy, but whatever. Okay, so we're going to do it again. Except this time we're given stuff that's in rectangular form, and we're going to convert it to polar form and then use the product theorem and then convert back. So there's a couple of conversions that are going to happen. So we're actually going to do this one two different ways. So the first one, we're going to convert it. So I'm going to deal with this section here, the 1 plus I root 3. And I'm going to draw a representation of that. So 1 in a positive x direction and root 3 in the positive y direction gives us something here in quadrant 1. So our x value here is 1, our y value here is root 3. And we have to come up with our R value and our theta value that would produce this. Now this is a 30, 60, 90 triangle. We should be able to recognize that by now. This root 3 tells us that that in that case is a 30, 60, 90, and we have the relationship. This angle, or this value here, would be x root 3, and this would be 2x. So our hypotenuse, or R value here, is going to be 2. And then that means that this angle is going to be across from my 60-degree angle. So my theta is going to be 60. So this part would be 2 cis 60. And we're going to do a same conversion except for this second one that we have. So that's negative 2 root 3 plus 2I. So negative 2 root 3 on our x values, positive 2 on our y values means that we are going to be in quadrant 2. So this is negative 2 root 3. This is positive 2. Again, that root 3 kind of tells us that we're probably dealing with the 30, 60, 90 triangle. So x root 2, 2x means that our hypotenuse is going to be 4. And across from then 2, if this is my hypotenuse, my short leg is always half of my hypotenuse. So that means like the 2 and 4 tells us that this is a 30-degree reference angle. But again, we are in quadrant 2 in this case, so it's not 30 degrees. Our R value is 4. Our angle to give a 30-degree reference angle in quadrant 2 is going to be 150, 180 minus 30. Okay, so now we're going to apply the product rule. Now that we have two things that are getting multiplied, this polar form, we take our two R values, which are 2 and 4, and multiply and get 8. And then we add our inside angles. So 60 plus 150 is going to be 210. Okay, so our answer is asking us to convert it, or our question says we want to convert it into rectangular form, and so far we just have something that's in polar form. So to convert it to rectangular form, we need a real and imaginary component, so we're going to draw yet another diagram. 210 degrees is our angle, so that's going to be in quadrant 3. That's a 30-degree reference angle. Our R value is 8. Across from 30 is half my hypotenuse, so that should be 4. And then across from my 60-degree angle would be times root 3. So 4 times root 3. And the last thing that you want to double check after you've come up with this 30, 60, 90 relationship is make sure that you're in the right quadrant. So both these things should be negative for our x values, and our y values, our real and our imaginary component. So our real component is the x value, which is negative 4 root 3, and our imaginary component is negative 4, and we tack on the I. Be careful, because this happens to me a lot, where I end up like looking across my triangle a lot, and I end up writing this is my real component and this is my imaginary component. So just double check and make sure that you're actually representing the right things. So the alternate way that we're going to do, instead of actually converting it to polar form and then getting something in polar form and converting back to rectangular form when we started rectangular form to begin with, is to go back to lesson 1 before we knew how to do any of that stuff and just convert it with some real component, represent this with some real component and imaginary component, which just means let's just multiply it out. Like, what if we did it that way instead? So I'd have 1 times negative root 3, which would be negative 2 root 3. 1 times 2i, which would be 2i. This is a little bit messy, but I root 3 times negative 2 root 3 means I'll have a minus. I'll have 2. Root 3 times root 3 is going to be 3. And then I have an I. And then the last one I'll have a plus 2 root 3. And then I and I will give I squared. So I'll simplify that. I have negative 2 root 3 plus 2i minus 6i. And then I squared we know is negative 1, so minus 2 root 3 here at the end. And then we're just going to combine all of our real components and our imaginary components. So here's my real components. Negative 2 root 3 minus 2 root 3 is negative 4 root 3, which is what we have here, so that's a good sign. And then 2i minus 6i is negative 4i. So again, we get the same answer doing it this way, and this might be easier, like in this sense, when we multiply two rectangular coordinates together. Multiplying is always easier than dividing, and so when we multiply these, it's not too bad to actually simplify it out. But if I were trying to like divide these two quantities, then my life would be a lot harder because I'd have to multiply by the conjugate. And multiplying by the conjugate to get that real and imaginary component definitely is messy. And so sometimes it's easier to do it this way, where we convert to polar, get something in polar, and then convert back to rectangular. Okay, so we're still going to represent for this one our answer in rectangular form. So far we've just done product stuff. So we're going to do this one for our quotient theorem. So our values here, like what I noticed right away is that I have a root 7 and a root 7 on top. So I'm going to get rid of those. And our quotient theorem tells us that we need to divide these two r values. So I already got rid of the root 7s. The 10 divided by 5 is going to be 2. And then our quotient theorem tells us, instead of the product theorem, to add the two x or the angle values, we need to subtract. And we always do like our top minus our bottom. So it might be tempted, because this is negative, to do 150 minus negative 60. That would give you a different angle. So it's always top minus bottom. So negative 60 minus 150, which gives us 2 cis negative 210. And you don't have to, but I like positive angles better. So instead of writing it as negative 210 degrees, I'm going to find the coterminal angle. So add 360 to it, and you should get 150 degrees. Okay, so we want to convert this into rectangular form, which means we need to draw a picture of what this actually looks like in polar. This is our angle, 150, which is in quadrant 2. But again, you could do like negative 180 and then 30 more degrees. Either way, you should be here and then quadrant 2. So a 30-degree reference angle is what we're looking at. Our R value here is 2. We've already done this rectangle, or this triangle before, 30, 60, 90. This is 2x, so this would be x, which is 1. Oops, sorry. And then this would be x root 3, which is 1 times root 3, so root 3. But we're in quadrant 2, so make it negative. So our real component is our x value, so negative root 3. Our imaginary component is our y value, which is 1. So plus 1i, or just I, for our answer. So you'll notice that all the stuff that we did today, where we're like converting from polar to rectangular, is super important, because we need to keep doing that when we're like moving on in this. So that was really like the foundation, which is why you had a ton of problems and got really good at it. It's because we need to do all those things and be really fast at it, so that we can go on and answer it in rectangular form and convert it from those things and do it pretty quickly. Okay, so in the back here we have a couple more examples that are a little bit more difficult. So these ones are again using the product, and we are going to give our answer in rectangular form, which is the x plus yi. But again, we have like a slight problem, because these ones both, like if we were going to try to like do this like we did in our first lesson, we would have to multiply by the conjugate of this, and that gets messy. So this one's actually a lot faster just to represent it in polar form and then use the quotient theorem. So let's tackle the top. We're going to convert both like this part to polar and this part to polar, so draw two different triangles. So our first one, 1 plus I root 3, would be 1 in our real component, root 3 in our imaginary. So it looks like this, 1 root 3. We've already done this triangle on the front too. This is a 30, 60, 90, x root 3. This is 2x, so it should be 2. Or you can use the Pythagorean theorem, but I would stress that you need to make sure that you can recognize those 30, 60, 90 triangles when you have them. So this angle here is going to be a 60-degree angle across from our root 3. So on the top here, converting that to our real component, or real numbers, sorry, our rectangular form, which is our real and imaginary components. From that to polar form, our R value is 2, and then our angle here is 60. Totally messed that up when I was saying it. Rectangular form to polar form, R and theta. Okay, let's do the bottom, which is the negative 2 root 3 plus 2i. I think we've already done this triangle in the top and the front too. So negative 2 root 3, positive 2 gives us this reference angle, or this reference triangle. Negative 2 root 3 is here, 2 is here. Again, 30, 60, 90 triangle, we've got a root 3 that's involved. So x root 2 or x root 3, and then 2x would be 4 for our hypotenuse. Double our short leg. This is our short leg since it's across from like our shorter side, across from the 1/2 version, not the root 3, in other words. So this angle in quadrant 2 is going to be 150 degrees. Our R value is 4. So we're dealing with that in our polar form. And then I'm going to come down here. I'm going to use the quotient rule, which means I'm going to divide my two R values. So 2 divided by 4 is 1/2. And then we subtract our angles. So 60 minus 150. So 60 minus 150 is negative 90. Which again, you can represent that in a polar form if you want, like you can, or sorry, a positive angle if you want, or you can just kind of draw what that would look like. So knowing that you go clockwise around your circle means negative 90 is 270 degrees. So this would be our vector. And again, just be careful because this one you're going down, so your imaginary component should be negative, but a lot of times we end up writing it as positive because we know that our magnitude here is positive, but your y value here is negative 1/2. So just be careful when you're looking at that. So your x component, you're not going anywhere, so you're 0. Your y component is negative 1/2, and then tack on the I, or you can drop the 0 and just represent it as negative 1/2 I. Okay, we're going to do that one more time in example 5 here. Again, like this one is a little bit more complicated as far as if I were asking you to write this into rectangular form, you would have to multiply by the conjugate, and multiplying by the conjugate of negative 6 root 6 plus 6i times root 6 to the top and bottom can get a little bit complicated, and it will take a lot of simplification to get there. I mean, it could be done, but we are going to do it with the polar form because it's a lot faster and because the directions tell us to do that, so we're going to do it that way. So let's tackle like the top part. We have negative 5 root 6 plus 5i root 6. So that would be located in a negative x value and a positive y value would be quadrant 2. Here's my vector. So negative 5 root 6, positive 5 root 6 for our x's and y components. Knowing that the x and the y values are the same, this is going to be a 45-degree angle. And that tells us that our hypotenuse here, when we deal with our 44, 45, 90 triangles, this is x root 2. So we would multiply this 5 root 6 by root 2. So we'll get 5 root 12. When we multiply those two things. And then that's something that we can break apart and simplify. So, 4 and 3 go into that. I can take the square root of 4 out and multiply by 2. So it'd be 10 root 3 in total there for that problem. So that's our R value. This is our theta value, 45 degrees in quadrant 2. So that means this is 10 root 3, and then cis 180 minus 45 is 135. So we've tackled that one. Let's deal with the denominator too. So negative 6 root 6 minus 6i root 6. So negative 6 root 6, negative 6 root 6 is going to be in quadrant 4, or sorry, 3. Negative 6 root 6, 6, negative 6 root 6. Again, we have an isosceles triangle formed here because both my x's and my y's are the same. So that means that I'm dealing with a 45-degree reference angle. So 180 plus 45 will give us the theta value that we need. To find our hypotenuse here, again, our R value that we're looking for, since it's a 45, 45, 90, we would multiply by root 2. So it would be 6 root 6 times root 2, which gives 6 root 12. And again, same thing, we can simplify this. And so we can pull that 4 out, take the square root, you get 2. 2 times 6 is 12, and we have that left over root 3. So 12 root 3. And then the angle in quadrant 3, 180 plus 45 degrees, is 225. Okay, I ran out of room, so I'm going to write this down here. We have 10 root 3 cis 135, 12 root 3 cis 225. And then we use the quotient rule like we just did. So one thing that I can see, like this is kind of like example 3, where we have like this kind of complicated mess. And the first thing that we did, since we have root 3 and root 3, is we can cancel those. Even if you didn't simplify this out, we would have had like 10 or 5 root 12 on top and 6 root 12 on bottom, and the root 12s would cancel. So like doing this process is good, but we still would have gotten the same answer if we left it that way. And then I'm going to reduce that down, so divide them both by 2 and you get 5 over 6. And then to use our quotient rule for that, we are going to subtract our values, subtract our angles. When we do that, we actually get negative 90 again. So again, like same picture as before, negative 90 is a direction that goes straight down from like going negative 90 degrees. This R value again is 5 over 6, but our Y value, our Y component, since we're going down, is going to be negative 5 over 6. And since we want it in rectangular form, it'd be 0, which is our X, plus negative 5 over 6 I, negative yi. So don't forget, like this still does have a, since it's still representing this imaginary component as a vector, we still need to put the I at the end. And then we can leave out this 0, so we can represent it just as negative 5 over 6i. Okay, last one. Again, this is something that we're going to use the product theorem rather than the quotient theorem that we've been looking at. Again, like this is something that we could multiply all out, but it gets really complicated, so instead we're going to convert it to polar form and then convert it back to rectangular form at the end. So let's draw some pictures for our first part. So negative 2/3, negative 2/3 root 3 means that we're going to be in quadrant 3. And I'm going to write out my, oops, my arrow looks bad, my real component, which is negative 2/3, and my imaginary component, which is negative 2 root 3 over 3. So again, what tips me off for this problem is seeing that we have a root 3 here, which means that we're probably dealing with a 30, 60, 90. So it's kind of zero in on that root 3, and that gives us this 60-degree angle here. And then we know then that our hypotenuse is always twice our short leg. So our short leg here is root 2 over 3, so our hypotenuse is going to be twice that, which is 4 over 3. So this part is 4/3 for our R. Our angle here is 60 degrees in quadrant 3, so 180 plus 60 is going to be 240. And then we'll draw the same one or same type of picture for our second one, so we can convert it to polar. So 9 root 3 over 2, that's some positive value. And then negative 9 over 2 is some negative value, so we are dealing with quadrant 4 here. My real component is 9 root 3 over 2. My imaginary component is negative 9 over 2. And again, I can see that relationship happening here where I have this root 3. So it means I'm dealing with a 30, 60, 90. So that root 3 is probably going to be across, or is going to be across this 60-degree angle down here in the corner. So that means that this is a 30-degree angle up here. So if I take my short leg and find my hypotenuse, my R value, I'd multiply by 2. So negative 9 over 2 times 2 is just going to be negative 9. Oh, sorry, positive 9. It will be negative 9, but our R value is always positive. So we have positive 9 for our R. So 9 cis, and then this angle here in quadrant 4 with 30-degree reference angle is going to be 330 degrees. Okay, product rule tells us we are going to multiply our two numbers here. So we have 4/3 times 9, and then we're going to add our angles. So we put them together in 1, 240 plus 330. So we'll reduce this, 4/3 times 9, so it can cancel out a 3, and I'd have 12. When I add these together, I'll have 570, which I don't like to deal with that, so I'm going to come up with the coterminal angle. So if I subtract 360 to this to come up with my coterminal angle, it would be 210 degrees. And that's easier to graph and easier to deal with for my reference angles. So if I draw that picture, 210 degrees is going to be in quadrant 3. So looks something like that. It's a 30-degree reference angle. I know that my hypotenuse of my triangle, my R value is 12. And so then I can use my 30, 60, 90 triangle relationships in reverse. So divide it by 2, and I get 6. And then take that value, tack on a root 3 to come up with my real component and my imaginary component. So all together in rectangular form, which is what we want, of x plus yi, my x value here is negative 6 root 3, and then my imaginary component is negative 6i. So there we go.